This video is the first of a couple of videos where we will discuss the difference in reactivity for different acyl molecules for nucleophilic addition or nucleophilic substitution. So let's remember the structure of an acyl group. And what this nucleophilic addition, which is also called nucleophilic substitution, we'll talk about why, what that general reaction scheme looks like. So an acyl group is a group where we have a carbonyl carbon is bonded to some carbon chain, and then this can have different groups here. So if that group is another carbon chain, then that's a ketone. If the group is an OH group, that's a carboxylic acid. If the group, and I'm talking about the group here, is a nitrogen, then that's an amide. If it's a chlorine, it's an acid chloride. So we're going to talk about all of those and the reactivity of those. And then when we have a general nucleophilic substitution reaction, we have some nucleophile. Of course, nucleophiles have electrons that can create a new bond. So we have some nucleophile that will add to the carbonyl carbon. So this is a nucleophilic addition step, but we call it also nucleophilic substitution because after a couple of steps, right, this is not the complete mechanism, we've now substituted whatever this group is for the nucleophile. So now the nucleophile is present here. So this is a very general reaction scheme, but this is an acyl group and what occurs when we have nucleophilic substitution. So now let's look at general reactions for carboxylic acid and carboxylic acid derivatives, and then the reaction conditions that are needed for nucleophilic substitution to occur in those molecules. So we'll write general reaction scheme . Ca, carboxylic acid, it's short for carboxylic acid. So we're talking about carboxylic acid derivatives. Since we've started the carboxylic acid unit, we've learned really about 4 derivatives: esters, amides, acid chlorides, and anhydrides. So those are the 4 that we'll be comparing, along with carboxylic acids. So we'll start with amides. So amides have the acyl group. This is the acyl group. And then bonded to the carbonyl carbon is a nitrogen, and that can have 2 different R groups. Those could also be hydrogens. So this is the amide molecule. If we are doing nucleophilic addition to an amide molecule to produce the nucleophilic substitution product, then for this reaction to occur, an acid or base is required. And heat is required. So for nucleophilic substitution to occur with an amide, an acid or base is required and heat is required. Next, we'll look at esters. Esters have the acyl group right here, and then an OR group. So if a reaction, a nucleophilic substitution reaction is occurring with an ester starting material, for these reactions, acid or base is required. And sometimes brief heat. So this indicates that esters are slightly more reactive than amides. Amides always require heat. Esters sometimes require heat. So it depends on the ester, but generally esters are more reactive than amides. Next, we'll look at anhydrides. Anhydrides have two acyl groups. They have a carbonyl. Carbonyl is bonded to an oxygen, and that oxygen is bonded to another acyl group. So if we're doing nucleophilic addition with an anhydride starting material, we don't have any required reaction conditions. Acids and bases are not required. Heat is not required. So that indicates that anhydrides are more reactive than both esters and amides. And then last, we'll look at acid chlorides. Again, we have the acyl group right there, and then carbonyl carbon is bonded to a chlorine. And if we are doing nucleophilic substitution with an acid chloride, again, no acid or base or heat is required. So this means that nucleophilic substitution reactions with an anhydride starting material and nucleophilic substitution reactions with an acid chloride starting material occur rapidly at room temperature, and we don't need acid or base. So both of these reactions, we'll write a little note here. Now, this doesn't mean that you can't add acid or base, so that you can't increase the temperature, but for the reaction to occur, neither are required. So if we look at all four of these now, amides, esters, anhydrides, and acid chlorides, we can write the trend in reactivity for these carboxylic acid derivatives. So I'll zoom back in. Based on reaction conditions required, amides are less reactive than esters. Carboxylic acids have very similar reactivity to esters because carboxylic acids also have that oxygen bonded to that carbonyl carbon. And then anhydrides and acid chlorides are both more reactive than amides and esters. So our trend, we have amides are less reactive than esters. Esters are approximately equally reactive as carboxylic acids. And then anhydrides are much more reactive. So we have the two symbols here. than esters and carboxylic acids. And acid chlorides are slightly more reactive than anhydride. Now, from what we've stated so far, we can't directly compare anhydrides or acid chlorides. They both seem to be very reactive. But in the next few videos, we'll talk about why acid chlorides are slightly more reactive than anhydrides. So the goal for the next couple of videos that you'll watch is to explain this trend in reactivity. So why is it that amides are less reactive than esters and carboxylic acids, and anhydrides and acid chlorides are more reactive? So we will look at a few features of these different functional groups to understand their reactivity.